All right, so we are now on lesson 16, which is actually the very last lesson in unit 4 of electrochemistry. And lesson 16 is about the electrolytic cell. And so in our last lesson, when we were talking about the galvanic cell, we were talking about spontaneous reactions that happen between metals, and this type of reaction that occurred spontaneously produced electricity. Now today we are going to talk about the opposite of this reaction that requires an input of electricity and occurs in special cells called electrolytic cells. And in this lesson we're going to talk about the components of electrolytic cells. Oh, here comes Borna. I'm going to let him in. Hi, Borna. We were just starting lesson 16 right now. So we are going to be talking about the different components of electrolytic cells. We're going to be talking about the relationship between time, current, the amount of substance produced or consumed in any electric process, and how that is governed by Faraday's law. And we are going to solve some problems applying Faraday's law. So Borna, what you missed and what I was saying is that today's lesson, we're going to be talking about electrolytic cells. And in electrolytic cells, the reaction occurs in the reverse, the opposite direction of the spontaneous reactions that we've discussed previously in galvanic cells. And in order for these non-spontaneous reactions to occur, we need to input energy in the form of electricity, and that these types of reactions happen in cells called electrolytic cells versus the galvanic cells that we've previously studied. Galvanic cells generate electricity. Electrolytic cells require an input of electricity. All right, so again, just to compare and contrast galvanic cells versus the electrolytic cell, galvanic cell contains a spontaneous reaction, whereas the electrolytic cell, it's a non-spontaneous reaction. In the spontaneous reaction of the galvanic cell, electron flows from a higher potential to a lower potential, and that's how it generates electrical energy. That difference in electric potential is the electric energy. It's the flow of electricity, the electrons, the current that is produced. In the electrolytic cell, we use energy to move electrons from a lower potential up to a higher potential energy. And the overall reaction in the electrolytic cell is non-spontaneous, and therefore it requires an external source of energy in order to make this happen. Now, because of the external voltage of the electrolytic cells, the electrodes in the electrolytic cells have opposite polarities, opposite charge in the electrolytic cell compared to what they are in the galvanic cell. And we are going to review that a little bit more in the next slide. And this is because we are forcing a redox reaction to happen. In the galvanic cell, the redox reaction happened quite spontaneously. In the electrolytic cell, we are forcing a redox reaction. The reaction in the electrolytic cells are the reverse of what happens in galvanic cells. I really want to emphasize that point. And so therefore they require a power source to provide energy to really push electrons towards the cathode and away from the anode. And in this case, in the electrolytic cell, the anode then becomes the positive charge and the cathode becomes negative. And the negative ions move towards the anode where it's positive and where oxidation occurs. And the positive ions now move towards the cathode where reduction occurs. So as an example, in the forward reaction of zinc atom plus copper ions going to copper atoms and zinc ions, this reaction is very spontaneous and it generates electricity. and zinc displaces the copper ions from the solution spontaneously. But in the reverse direction, which is the situation you have in the electrolytic cells, you have copper atoms and zinc ions, and you won't get a reaction. The copper ions displace zinc. Displacing zinc is not a reaction that will occur spontaneously. You don't get a reaction. You need an input of energy to get the reaction to occur. So let's really compare the galvanic and the electrolytic cells. And here I have a diagram of the galvanic cell on the left and the electrolytic cell on the right. And so notice that in the galvanic cell, the electrons are flowing from the anode, which in this diagram is the zinc. They flow spontaneously towards the cathode, which is copper. And notice in the electrolytic cell, the flow of the electrons is reversed, is flowing in the other direction. It's flowing, instead of from zinc to copper, it's being forced to flow from copper towards zinc. And this is due to the presence of a battery. We need a battery to provide the energy to do that. And that any galvanic cell that you have set up can be converted into an electrolytic cell just by putting in a battery. So remember that copper and zinc are metals, and metals react by losing their electrons. Zinc has the ability to lose electrons more readily than copper. And that's why in the galvanic cell, it spontaneously loses its electrons towards copper. Copper asks for the electrons, wants the electrons, and zinc tends to lose them quite readily towards copper. And the electrons from the zinc electrode overpower the electrons trying to leave the copper electrode. So that's why you have a flow of electrons in this direction. Now the battery here in the electrolytic cell provides the energy to push the electrons away from the copper electrode towards the zinc electrode. And the battery has to be positioned in such a way that the negative end faces the zinc electrode and the positive end faces the copper electrode. And then the flow of the electrons in this battery is always from the positive terminal towards the negative terminal. And that this is how the reaction occurs in this non-spontaneous manner. So here I've just listed, just briefly, point form, the differences between the galvanic versus the electrolytic cell. So what you have to remember, in the galvanic cell, the reaction is spontaneous. In the electrolytic cell, it's non-spontaneous reaction. In the galvanic cell, our anode is negative, and it is the zinc. Our cathode is positive, it is the copper. And we have oxidation at the anode, where zinc is oxidized to zinc ions and the release of 2 electrons, whereas reduction occurs at the cathode, where copper plus the copper ion plus 2 more electrons is converted into copper, which then deposits on this copper electrode. And so entire cell reaction can be described as zinc atom plus copper ion goes to copper atom and zinc ion. Now in the electrolytic cell, this reaction is reversed. It's a non-spontaneous reaction. And in fact, the electrodes are switched. Now in this case, the copper is the anode and is positive, and the cathode is now the zinc and negative. And the oxidation occurs at the anode, and reduction occurs at the cathode. Reduction always occurs at the cathode, oxidation always occurs at the anode, both in the galvanic cell and the electrolytic cell. Remember, ox, right? Anode oxidation, cathode reduction, cat, red, red cat, and ox, red cat. And that's the case for both electrodes. It's just that in the galvanic cell, it's the zinc that is readily pouring the electrons towards the copper, but in the electrolytic cell, copper is being forced to give up its electrons back towards the zinc. And so now the overall reaction is this. See, copper and zinc ions are in this reaction becoming zinc and copper ions. Copper is being forced to donate electrons towards the zinc cathode. So in this example, this following reaction takes place in an electrolytic cell. So that tells you right away that this is not a spontaneous reaction. So write the oxidation and reduction half reactions in part A, and in part B, show this reaction in shorthand notation. So the solution, step by step, you go through it. As before, you assign oxidation numbers to each of the reactants and products. So anytime you have an element in its non-combined state, such as this copper atom, the oxidation number for that is always 0. Same with this nickel. This nickel in its non-combined state, the oxidation number is always 0. And I just want to put this here to make sure it's complete. All right. And then anytime you have an ion, the charge on that ion, so this nickel ion, the charge on that ion is simply the oxidation number of that ion. So if it's an uncombined ion, it simply is the charge on the ion. Again, this copper ion, this aqueous copper ion, the charge on it is simply the charge on this copper ion. So the oxidation number is +2, and here the oxidation number is +2. Now, notice that in the beginning, in the reactants, copper started out with an oxidation number of 0. And this oxidation number now increased to 2, to +2. So because the oxidation number increases, it is undergoing oxidation. So copper is becoming oxidized. And since the oxidation number of the nickel ion is decreasing, so it started out with 2 and it's going down to 0, line it up right underneath nickel to make sure it's clear. So therefore, because it is becoming decreased or reduced, it is undergoing reduction. Look, the oxidation number is going down. It's becoming reduced, so it's becoming reduced. Then we write down these oxidation reduction half reactions. That's what it asks for. Write the oxidation and reduction half reactions. Okay, let's write it. What got oxidized? Well, it was the copper going to copper ion. So copper goes to copper ion, and of course, it also has to lose 2 electrons in order to become go from a neutral charge to a +2 charge. It has to lose 2 electrons. And that's our oxidation half reaction. And our nickel ion is going to nickel atom. And of course, to go from a charge of +2 to a neutral charge, it has to gain 2 electrons to cancel out this +2 with 2 minus electrons to become a neutral nickel atom. And this is our reduction half reactions. So there we go. We've answered this part A, write the oxidation and reduction half reactions. Then in part B, we are asked to write the shorthand notation, and the shorthand notation follows the same rules as before. We write down our oxidation on this side, and we separate it with a double line from the reaction reduction reaction on this side. Okay. We always write the reaction that's happening at the anode on the left side, and the reaction that's happening at the cathode we write on the right side. Okay, there's a couple of support questions for you guys to work through. Now let's talk about what are some of the applications of these electrolytic cells. So electrolytic cells have applications in, for example, electrolysis, recharging batteries, refining metals, and electroplating. These are just some examples. So electrolysis has got many useful applications. Electrolysis of water. Electrolysis means splitting by electricity. Electrolysis of water produces oxygen and hydrogen gas, and this would be the reaction for it. You have two molecules of liquid H2O and plus the energy of the electrolytic cell, and it produces two hydrogen molecules, two molecules of hydrogen gas, and two molecules of oxygen gas. The oxygen and the hydrogen gas that's produced from this electrolysis has got lots of practical applications. For example, the oxygen can be used for the production of pulp and paper, and it's also sold to patients as oxygen tanks, patients with respiratory problems. Hydrogen can be used to generate electricity and to power electric buses and cars and motor vehicles. Electrolytic cells are also used along with galvanic cells to recharge batteries in a cell phone or in a car. So anytime you're recharging your battery, you are using the chemistry of an electrolytic cell. Electrolytic cells are also used in metal refining. Many of metals that we find aren't found in their pure elemental form in nature. Wherever they're mined, it's not a pure source of that metal. For example, aluminum, that when it's found in nature, it's found in a rock, and this rock is called bauxite. And bauxite contains this molecule called aluminum oxide. So it's not pure aluminum. You can use electrolysis to isolate pure aluminum from this bauxite, from this aluminum oxide. And then that purified, refined aluminum metal has got many applications, such as in construction of aircrafts and boats and pop cans and construction material and so on. Then there is also the utility of electroplating. Electroplating is a method that's used when you want to produce something shiny coated with a certain metal. For example, we have light fixtures and doorknobs and door handles and whatever, and oftentimes inside there's a different metal, and then it's electroplated with whatever metal that you want to see as your finish, whether it be nickel or brass or what have you. And also electroplating is very useful in making jewelry or cutlery. You can have silver plated cutlery, you can have gold plated jewelry, even in things like motorcycle fenders or even coins. Money is electroplated. So yeah, during the process of electroplating, these objects that are made mostly from less expensive metals, such as steel, are then electroplated to apply a thin layer of a more precious metal, such as nickel or gold on top of it.
Sorry, miss, my laptop got disconnected.
Oh, that's okay. So here's a diagram that shows, for example, silver plating of a spoon. silver ions from this solution gain electrons and are reduced, and then the ions solidify on the cathode, which is the spoon. And then the solid silver anode loses its electrons. So that's how you get transfer of silver ions onto the cathode, which is the spoon. And notice that this is an electrolytic cell and it has the presence of a battery. Okay. There's some drawbacks to electroplating. Many of them are environmental. Well, as you can imagine, electroplating consumes electroplating and electrolytic cells consume an incredible amount of electricity because you have to overcome this non-spontaneous reactions and push the electrons from a lower energy level to a higher energy level. It doesn't happen spontaneously, so it consumes incredible amounts of electricity. And if you have factories that manufacture products using this electroplating technique, although most of them happen to be located usually on water where there's a source of hydroelectricity, a lot of times these the electricity generated in a place like Ontario here is often through the combustion of fossil fuels. So you have fossil fuel combustion in order to provide the energy for these electroplating methods. And fossil fuels, as you know, when you burn fossil fuels, you produce carbon dioxide. And you recall from our previous lesson that excess carbon dioxide leads to the greenhouse gas effect and produces acid rain. So both of these things are very detrimental to the environment. Also, the process of electroplating can also cause cancer for workers that are exposed to some of the chemicals that are used in this process. So altogether, it has some drawbacks. Now let's talk about Faraday's law. Michael Faraday made a major contribution to chemistry by making the connection between stoichiometry and electrochemistry. And this concept relates directly to the extraction and refining of many metals through electrolysis. So what is Faraday's law? In Faraday's law, the amount of substance produced or consumed in an electrolysis reaction is directly proportional to the quantity of electricity that flows through the circuit. So what does that mean? That means these two equations. And in these two equations, you can see that there's a relationship between the amount of charge, and that's equal to the amount of current multiplied by time. There is a Faraday's constant, F, and F is the quantity, the amount of electric charge on 1 mole of electrons. And that 1 Faraday is defined as 96,500 coulombs per 1 mole, per mole of electrons. So 1 Faraday is equal to 96,500 coulombs per mole of electrons. And if you remember the flow of electrons, if you remember it from previous courses and physics, and flow of electrons is called electric current. It's given a symbol I, and it is measured in amperes. The quantity of electric charge, so how much electric charge there is referred to, is given the symbol coulomb, and is equal to the current multiplied by time. So the amount of the quantity of electric charge is equal to, which is measured in coulombs, the unit for that is coulombs, and the symbol for that is Q, is equal to current, which is given the symbol I, and the units for it are amperes, A, multiplied by time. Time is always given the symbol lowercase t, and the standard unit for measuring time is in seconds. So coulombs is equal to amperes times seconds, or amperes is equals to coulombs per second, if you rearrange this equation. So this is Faraday's law. How can we apply Faraday's law to solving some chemistry problems? For example, you might be asked, calculate the mass of aluminum produced by electrolysis of molten aluminum chloride if a current of 500 milliamps passes for 1 hour. So you're given the current. So this is your I value, and it has the unit amps. Here it's milliamps. So you're going to have to remember to convert milliamps into amps. And you have a time value. Your time is 1.5 hours. And the proper standard time unit for these equations is seconds. So you have to remember to convert your time into seconds. So what are we given? We are given the electrolyte is this molten aluminum chloride. So the electrolyte is AlCl3, aluminum chloride. In liquid form, it's molten. So the reduction half reaction is that you have, and this is electrolysis. So you write the half reaction. So here you have the ion, the aluminum ion, and the aluminum ion is going to get, through electrolysis, it's going to become solid aluminum atom. And in order to do that, aluminum will have a charge of +3, because look, there's 3 chlorides and chloride has a charge of -1. So therefore your aluminum will have a charge of +3. So 3 minuses here on the chloride, and on the, rather 3 minuses on 3 chlorides. So Cl minus times 3, so you have 3 minuses, and so therefore your aluminum is going to be 3+. And that then gains 3 electrons to become solid aluminum atom. So the molar mass of aluminum is 27 grams per mole, and you can find that on the periodic table. There's nothing magical about it. You just look up the relative molar mass of aluminum and the current that then is being applied. The current is 500 milliamps. So we have to convert this 500 milliamps to amps. And how do we do that? Well, we have to divide it by 1,000, a factor of 1,000. So anytime you have any unit that's in milli, and you want to bring it back to its standard units, whether it's meters, if you've got millimeters and you want to bring it to meters, whether it's milligrams and you want to bring it to grams. Same thing here, it's milliamps and you want to bring it back to amps. So you divide it by a factor of 1,000 and it becomes 0.5 amps. Now the time of 1.5 hours, you convert it to seconds. And if you convert 1.5 hours to seconds, you'll see that it is 5,400 seconds. And what do you require? You require to know what is the mass of aluminum. That's what the question was. Calculate the mass of aluminum produced by this electrolysis reaction of a molten aluminum chloride once you pass a current of 500 milliamps for 1.5 hours through it. So these are the equations at our disposal. This is the equation that relates charge to current and time. This is the equation that relates charge, coulombs, Faraday's constant and the number of moles. And this is the equation that relates mass to number of moles and the molar mass right here. So we have these relationships in our toolkit, in our equation toolkit, and we know how to use them. So we want to find out how many coulombs of charge are passed into this electrolytic cell. How do we find that out? Well, we know that 0.5 amperes is applied for 5,400 seconds. So we multiply that, and that gives us 2,700 coulombs of charge has passed through this electrolytic cell. Now we want to know how many moles of electron are found in 2,700 coulombs of charge that passed into the cell. So the number of moles of electrons that are from this 2,700 coulombs of charge. So number of electrons is this value Q that we calculated, coulombs, divided by Faraday's constant, which has the units coulombs per mole. And if we see, the coulombs cancel out, and we're left with how many moles of electrons? And we're left with, there's 0.28 moles of electrons present. Now, how many moles of aluminum do you get from this 0.28 moles of electron when you're reducing this aluminum ion? So it's just a one-to-one relationship, because we see that the relationship between here is for every 1 aluminum, we need 3 moles of electron. So 1 mole of aluminum to 3 moles of electron is equal to how many moles of aluminum? To 0.028 moles of electrons. And we do the math, we multiply and divide, and we know how many moles of aluminum we have now. Then we can take this number, knowing how many moles of aluminum we have, and knowing the molar mass of aluminum is 27 grams per mole. So we multiply those numbers together, and moles cancel out moles, and we're left with how many grams of aluminum. And we finish in the statement saying the mass of aluminum produced is 0.252 grams. And that's how you would solve this type of a question. This is how you would apply Faraday's law, the relationship between how many coulombs per mole, that's Faraday's constant. And so that's what that statement was saying about, it's the relationship between stoichiometry, so numbers, how many moles to how many moles, and electrochemistry. And that's what Faraday's constant gives us. That's what Faraday's constant provides for us. Okay, so there's a support question for you to practice with. It's very similar to this type of question. A little bit different. It's not asking for the mass of something. It's asking what amount of electrons is transferred in a cell that operates for an hour or an hour and a quarter, 1.25 hours, at a current of 0.15 amps per milliamp. So this is the current that's being applied. And I urge you to practice with these questions. And finally, we have our key question, which is due by Sunday, November the 14th. 3 questions. One is describe the 2 differences between galvanic and electrolytic cells. Again, if you refer back to the notes, you should be able to come up with at least 2, if not several more differences between the galvanic and electrolytic cells. But the 2 major differences are very obvious. I mentioned them several times. So go back and look at your notes again. Number 2, if you have 2 half cells in a galvanic cell consisting of one of them is iron electrode in a solution of iron sulfate, and the other one is silver electrode in a solution of silver nitrate. Part A and B, assume that the cell is operating as a galvanic cell and then state the overall half cell reactions. Describe what will happen to the mass of the electrode when the cell is operating. And then in part B, repeat part A. So say all of that, but assuming that the cell is operating as an electrolytic cell. Again, you shouldn't have any problem answering these questions either, just by looking back at our notes and understanding that this setup is the same as this setup, except instead of zinc and copper, you have, what do you have? You have iron and silver. Okay. And then the final question is one of those calculate the mass of this electroplating type of questions, which we went through an example here in great detail, and you should be able to do this, except that this time you're being asked about electroplating zinc. So you should have no problem doing these three key questions. Now, this key question number 16 is due Sunday, along with key question 15, the ones from last lesson on the galvanic cell. So this Sunday, you have key questions 15 and 16 that are due. Okay, let's take a look. We've got a whole hour left. So if you guys have any questions, we can look at whatever questions you have. And I can even open up last lesson on galvanic cell just to jog our memories. We can have a quick look at what were the types of key questions that you're supposed to be answering. Okay, so we did look at galvanic cells and in great detail. And this is a very useful memory tip to always remember that oxidation occurs at the anode and ox. Here, picture an ox in your head. And that reduction always happens at the cathode. Picture a red cat and ox. Oxidation at the anode, reduction at the cathode. And let's see what the key questions like. Okay, so the key questions, not too many. So consider this redox reaction, write the oxidation reduction half reactions. Again, just refer back to the slides that we discussed, and you should have no problem writing the oxidation reduction half reactions. And then do a sketch of the cell. Just sketch the galvanic cell just like we have in the picture. Do a quick sketch and label all the elements that you're asked to label. So if it says label the anode and the cathode, make sure you clearly label this is the anode, this is the cathode, and the direction in which the electron flows. Use an arrow, show me the direction the electrons flow. And then write this reaction in shorthand notation. And if you just refer back to the slides where we talked about shorthand notation, very simple rules. Always write the oxidation, always write the anode reaction on the left. And at the anode, you always have oxidation. And write the cathode reaction on the right. At the cathode, you always have reduction. And ox, red, cat. Just keep this picture in mind, and you should have no problem writing the shorthand notation, both for this and for the key question 16 for an electrolytic cell. Both for a galvanic cell and an electrolytic cell, you apply the same rule. Anode is always shown on the left, cathode is always shown on the right. And then you have a single bar separating the oxidation reaction from the reactants to the products, and a single bar showing the reduction reaction. Again, going from the reactants to the products. Question, a thought question. Think about it, read about it, talk about it, and reason. Give me your reasons as to what you think. It's worth 4 marks. Some people think it's better to leave a car outside overnight during the winter. Some people think it's better to leave it inside in a warm garage, especially if salt is used on the road. Give your reasons for and against this claim. What do you think? Do you think it's better to leave a car inside a warm garage during the winter? Or do you think it's better to leave it outside in the cold overnight during the winter? So give me your reasons and explain why you think, yes, it's better to leave it in the garage, or why you think, yes, it's better to leave it outside in the cold.
I say maybe in the garage so it stays like not warm, because like when you turn on the engine and everything, it's gonna try to get hot as well anyway. So it's like staying kind of warm is gonna like doesn't change it suddenly from cold to warm.
Okay, so what I want you to do in this question, so this is not just a question that's unrelated. We are talking about this question in the context of electrochemistry, right? Electrochemistry, and we talked about standard cell potentials, and we talked a little bit about corrosion. So what happens in the winter here in Canada? They sprinkle salt all over the place to help melt the ice. So think about it. If you want to sort of avoid corrosion, I think that's what is at the heart of this question, is that what's better for your car? Given that there's salt used on the roads, you think it's better to leave your car outside overnight in the cold, or do you think it's better to leave it inside in a warm garage? And give your reasons why. Keeping in mind corrosion, keeping in mind electrochemistry. So yeah. Now, number 3, a voltaic cell or a galvanic cell is constructed using electrodes based on the following half reactions. Okay, so you have given these half reactions. Which is the anode and which is the cathode in this cell? 2 marks. And what are the standard cell potentials? Okay, so you have to look at these, and you know on the charts, they're always written as reduction reactions, but look at the charts and describe which one is the anode and which one is the cathode in the cell. 2 marks. And then what is the standard cell potential? And we discussed how to calculate standard cell potentials using 2 different techniques. So you should have no problem calculating the standard cell potential for this last question either. Okay, so this one and this one due Sunday, November 14th. I suggest you start doing these right away. I know that the workload for this course is grueling. I understand that. And I understand that you guys are loaded with coursework from other courses as well. But that's what grade 12 is all about figuring out how to balance your work, how to organize your time, how to prioritize, how to get everything done in an impossible amount of time. And I very much sympathize with you, but it is doable. So yeah, if you guys don't have any questions, we can finish this lesson early tonight, and you can use what's left of the hour until 8, which you would have been in chemistry anyways, to get a head start on doing your key questions so that you could have them handed in and ready ahead of time even. Okay. I have been marking and returning key questions in addition to midterms. So Borna, I haven't marked your midterm yet, but soon. And yeah, midterms, key questions, it all is being returned to you in your Google Drive. So go ahead and look there and find out your marks and how you're doing in the course. If you want to discuss any of your marks or any of your assignments, no problem. I'm free, I'm available, and we can talk about it and figure out how we can improve on it, okay? All right, so actually, Borna, do you mind if I talk to you for a few minutes after class? And if there's nothing left, we can end this class for everybody else, for Sasan. I mean, it's just Borna and Sasan here today. Any questions, Sasan?
No, nothing.
Okay, all right then. Have a good night.
Thank you. Have a great night.
Thank you, you too.
Goodbye.
Bye-bye. All right. Borna, can we talk a little bit about how you're doing with your course load and your work and how things are coming along?
Yeah.
Okay, so I'm just going to finish the, I'm going to stop the recording.